Today's lecture is going to be devoted to a topic that you probably already know something about, namely the metric system of measurement. You probably know that scientists do not typically use English units like pounds or feet or inches when they're involved in whatever kind of work or research they might be doing. Instead, they use the metric system. Indeed, most of the world outside of the United States uses metric units for everyday quantities like distance, speed, weight, or temperature, for example. That's why if you are outside the United States, you will typically see distances posted in kilometers, kilometers, instead of miles. You will see temperatures expressed in degrees Celsius instead of degrees Fahrenheit, weights in grams or kilograms rather than ounces or pounds, and volumes in liters or milliliters instead of quarts and pints. The United States, for whatever reason, seems to lag behind in this regard. Now, when I introduce the metric system to my students, almost invariably, one or more students will say with total sincerity, "Boy, I hate that metric system. That is so difficult. The English system, our system, if you're living in the United States, that's easier." And they really believe this, probably for no better reason than the fact that they've grown up with these units for their entire lives of perhaps 15 or 16 years, so they are both familiar with them, and they may even have, although this is often actually not the case, a pretty good intuitive grasp of what an inch, a mile, a pound, a quart, or anything else really represents. But what is simpler about a system of measurement where you have to remember there are 12 inches to a foot, but 3 feet to a yard. Oh, and 5,280 feet to a mile. There's 2 pints to a quart, but there's 4 quarts to a gallon. There's 16 ounces to a pound. Oh, unless you're talking about fluid ounces, then there's 32 ounces to a quart, but those ounces have absolutely nothing to do with the other kind of ounces. Now, this to me is a very complicated system of measurement. What happened historically is that measurements were created in a very helter-skelter fashion, and they were often very imprecisely defined, often based on what seems today to be a rather odd choices. I mean, like the foot, literally being the length of a person's foot. I mean, that's hardly something that's very reproducible. By the late 1700s, it became increasingly clear that there was a great need for a system of measurements whose units were clearly defined, reproducible, and consistent across the world. Things had, in many cases, really gotten kind of ridiculous. I mean, for example, there was a unit called a grain, whose origin dated back many years. It was literally the weight of a grain of wheat. Now, in France, there were 9,216 grains to what was called a pound. Oh, but in England, there were 7,000 grains to a pound. Oh, that's unless you were an apothecary, what we would basically call a pharmacist today. Then there were only 5,760 grains to a pound. Well, you can imagine trying to conduct commerce between nations with such a messed up system of measurements. So in 1791, when I was just a little boy, a committee of the French Academy of Sciences decided to sit down and create a logical, coherent, and reproducible system of measurement. And by 1795, they had worked out that system of measurement, and we, of course, know it as the metric system of measurement. Now, the metric system has certain advantages. All fundamental units are defined in terms of things that are easily and accurately reproducible. For example, the meter was defined as 1/10,000,000th of the distance along a particular line or meridian between Dunkirk and Barcelona. But the actual standard was a platinum bar with polished ends. The length of that bar from end to end at a certain temperature was the official length of the meter. Prototypes were later made so other countries could have their own copy of the official meter. Later, this was changed to a platinum iridium bar with 2 graduation lines that were, by definition, 1 meter apart at 0 degrees Celsius. Secondly, they decided that all conversions within the system could be accomplished by simply moving a decimal point. things would either be 10 times larger or smaller, or 100 times larger or smaller, or whatever. And that's a whole lot simpler than 12 inches make a foot, but 3 feet make a yard, and 5,280 feet make a mile, etc., etc. So this became the International Metric System. Now, most students seem to believe that the system that was set up in the 1790s is still the one in existence today, but that isn't quite true. The system had flaws. There were some small errors made in setting up the original standards, and in addition, some of the standards were based upon objects that could be lost, damaged, stolen, or destroyed. For example, the bar that defines the meter, if that bar is stolen or damaged, we obviously have problems. As years passed, it became increasingly clear that the metric system could use some revisions and modifications. So an international conference on weights and measures was established. What emerged from this is what is now called the SI system. SI stands for Système International des Unités. Great French accent there, but we'll just call it the SI or metric system. This system is much like the original metric system, but there are some important differences. Here's one key difference. One great annoyance that had developed over the years that the metric system had been in use, was what you might call a proliferation of units. Units had been added and added and added until there often were several different units for measuring the same thing. We had ergs and we had joules for energy. Oh, and calories as well. We had newtons and dynes for force. We had angstroms, debye's, barns, ESUs, etc., etc. They decided they needed to clean up the system and cut down on the number of units. So they made a very interesting decision. They decided that they were going to determine exactly how many of what might be called fundamental units were actually needed to set up an entire system of weights and measures. And they were going to keep this number of fundamental units to an absolute minimum. Every other unit, and there are hundreds of units, every other unit was going to be derived from these fundamental units, which were called base units. Now, it has always fascinated me to think about how many fundamental units you would need. My intuition, honestly, is not very good here. I mean, I know the answer. But if I had to sit down and come up with an answer myself, I don't think I'd have much of a notion. How many base units do you need to derive every other possible unit in science? 2, 10, 25, maybe more? Although it actually took some time, it was eventually decided that 7 base units were needed. The base units cannot be derived from other units. They are fundamental units, very carefully defined. The derived units, while well defined, are not fundamental. They can be derived from the 7 base units. I'd like to make a comment here about the fundamental units. If you research the history of some of these units, you'll learn that some of the definitions of these units have actually undergone several revisions over the years. For example, as we said earlier, the meter was originally 1/10,000,000th of the distance of a particular meridian on Earth. Then it was the length of a platinum bar. Later it was the distance between 2 marks on a platinum iridium bar. But like we said, bars can get lost or stolen, so an effort was made to base this length on something in nature that would never change. This led to the meter being defined as, and this always sounds kind of funny, 1,553,164.13 times the wavelength of a particular line in the spectrum of a particular cadmium atom. Whether that really makes any sense to you or not really doesn't matter. The point is simply that the wavelength thing will never change. So no matter what might ever happen, With this definition, scientists could always reproduce an accurate meter distance. Later, that was actually changed to 1,650,763.73 times a particular wavelength of a particular kind of krypton atom. That could be measured with even greater accuracy, evidently. Why all the changes? Well, the idea is to get the most accurately reproducible standard possible. Today, the definition of the meter is different again. The meter is now defined as the distance light travels in 1,299,792,458th of 1 second. That's a pretty short time, but light travels very, very fast. If you let a beam of light travel past you for that tiny fraction of a second, it will have traveled 1 meter by definition. There was, and still is, great effort being devoted to trying to establish the most accurately reproducible standards possible and to remove all of these definitions from anything that could be damaged, destroyed, or changed. Today, all but one of the base units is defined in a way that references something that cannot be changed or altered. For example, it is believed that the speed of light will never change. So by defining the meter as the distance light travels in a certain amount of time, the meter will for all times both remain the same and the distance will always be reproducible with great accuracy. The only exception is the kilogram. There still exists an actual kilogram kept at the International Bureau of Standards, with many countries having copies. This is considered to be a very bad thing, and research is still going on to try and find something in nature that would never change and that could be measured to an accuracy greater than the accuracy with which we can measure the mass of the standard kilogram. That goal had not yet been achieved when this video was made. The new system, of course, still retains the idea that all conversions within the system can be done in powers of 10. In other words, by moving a decimal point. So what are these 7 base units from which all other units can be derived? They decided they definitely need a fundamental unit of length. It is the meter. Here is a meter. Well, a replica of a meter, pretty close. They found that they did need a unit for mass. And the mass that they chose is the kilogram. Now, this actually bothers some scientists. In fact, it appears to have bothered the people who established the system. But they decided that because of the history behind this unit, they would leave it be. Now, you might ask, what's the problem? Well, the entire idea is that you have fundamental units and prefixes that are supposed to tell you how many or what fraction of a fundamental unit you have. There's a verbal problem here. If this is a fundamental unit, it shouldn't be called a kilo anything. One could argue that it should have been given a new name. The fact that when you say kilogram, there is an implication that the gram is the fundamental unit of mass, and you are taking 1,000 of them. But that's not the case. The kilogram, despite its name, is the fundamental unit of mass in the SI system. The fundamental unit of time is the second. The fundamental unit of temperature, believe it or not, is not degrees Celsius. Rather, it is something called the Kelvin. They found that they needed an amount of a substance, and the unit that they chose was the mole. All of these units can be abbreviated. Meter becomes M, kilogram becomes kg, second becomes just S, not SEC, as many people